Fourier transform is tau over 2 sinc squared omega tau divided by 4. This is number 19 on page 702, table 701. So the fact that it's number 19 means that there's at least 18 before it. So you should open up the table and look at the table, look at the different functions that are there. I'm not going to cover them all in class if you do that. Just highlighting the important ones, or more used, I shouldn't say important, more used functions. Any insight about this? What are the zero crossings here?
N tau over 2.
Yeah, well, it's going to be n pi, right? That's when the sign is going to be 0, equal to omega tau over 4, solving for omega. That's equal to n4 pi, what, over tau? Okay. What do we have for the right? Well, wait, maybe even before we say that, let's guess. Let's guess. Is this signal going to need more bandwidth or less bandwidth than the rep function? Less. And why do we think less?
Less area.
Less area? That's good. Even though I made a mistake and couldn't find out my how, what is the area related to here? It's going to be the DC value again, right? So this is definitely half the area that we had before. So I would expect the DC value to be half of what it was before. And before we had tau, right? And so it used to be with the rectangle, it was tau times that. So we got half the area, so we're getting up half here. So that's good. I just don't know where the tau comes from yet. Did you get that point? So the area here dictates what the DC value is. Not necessarily the frequency content, where the zero clusters are. It turns out for whenever there's a rapidly changing time domain signal, when everything happens very fast, there's a fast transition that requires more frequency. So when, for example, the pulse got shorter, it went on, it went off on, and then on to off, quick, right? So we needed a lot of bandwidth, a lot of frequency to get those quick transitions. When we went on, left it on for a long period of time, and then went to off, right, we could do it in a very small frequency, so that the rapid, it wasn't changing as rapidly. So whenever you see a signal with rapid changes, your mind should go, oh, I need a lot of frequency, I need a lot of bandwidth for that kind of signal. Are there rapid changes here as there were in the previous one? No. This doesn't change as quickly as that, right? So it gradually comes up, then it changes and comes back down. Right? Where the other one went from nothing to on to nothing. So by that, I would say we definitely don't need as much bandwidth for this signal. So what do we have for the rec function? For the zero crossing?
Pi over tau.
2N, pi
2N.
over tau.
And that's what, you see that here? What does this mean? So when n is equal to 1, we get 4 pi over tau, 2 pi over tau. Oh, I also have the function squared. So I can't do an apples to apples comparison. Because it's not sinc, it's sinc squared. You just have to trust me that if the area under the curve is going to be less in the sinc function squared than the sinc function. So this signal is going to require less bandwidth to transmit, the triangle function, than square root. So why wouldn't communication systems do that? We just talked about the problem with dial-up modem. All right, so we had your to do that signal requires more bandwidth. Than that signal. But this signal is used all the time, and this one isn't. Why would that be? Just turns out it's easier to do on and off, or plus and minus, than it is to do a linear or ramp here, right? And it's easier to detect. Right? I can know here I'm at this level for a long period of time. Here I'm at for a short period of time. So I have to have different kinds of circuits to detect when I'm at these peaks and stuff. Or if I'm at a level and hold it for a while, I can integrate and collect all this energy and then say, oh yeah, you're a 1, or oh yeah, you're a 0. Or here it becomes harder to do that. The other interesting function is an impulse function. Delta t. So it only has value of t equals 0. Fourier transform. It is a constant value of 1. 0. Remember we talked about when the pulse width got smaller and smaller and smaller, the signal needed more and more and more bandwidth. Because there's 1 over tau relationship. But here the pulse width is 0.